Hi, in this video, we want to take a look at decision trees. All right, so what a decision tree does, it takes a predictor variable and it compares that to a target variable, and then it splits the predictor variable into two groups, and with the goal of getting more similar target variables associated with the predictor variable groups. That's a lot of words, But so basically, here's the idea. Take all of our data, and we're going to find some feature to split all the data on. And we want to do that so that the target variables here are more similar to each other, and the target variables here are more similar to each other. So like over here, we'll have like the larger values. Here, we'll have the smaller values. Or then what the decision tree is going to do, it's going to split this part again with the same technique. And it's going to split this again with the same technique. It's going to keep on splitting and splitting and splitting and splitting until there's no point in going any further. Okay, so something about decision trees is that they can overfit very easily. Honestly, they're not our best predictors, but when they're used in ensemble methods and they're used, like in random forest and stochastic gradient boosting, then they perform very well. My opinion is that the best thing for a decision tree, honestly, for us is to understand it for the other models, but also if I need to explain a random forest, I don't explain the random forest, I build the best decision tree I can, and I explain that, and I leave it as is. So a random forest is a forest of decision trees. It's a collection of decision trees, and gradient boosting is where we make a decision tree, we look at the error in our model, we build a new decision tree to correct that error. Then we look at the new error that we have. Then we build a new decision tree to correct that error. And we keep on doing this. So this error correction feature is what's called boosting. Now, random forest, there's no connection between one tree and another, while boosting is adapting off of previously built trees. Random forest, the decision trees are too deep. Gradient boosting, they're too shallow, and decision trees, we try to get it just right. All right, so let's go ahead and take a look at some code to be able to do a regression decision tree. And we're going to be using the Candy dataset again. So let's get Seaborn, Matplotlib, NumPy, and Pandas. All right, let's go ahead and read in the Candy data. Remember, this is the data set from looking at two candies from head to head. How many times did each candy win when it was put head to head against others? If you take liberal arts mathematics, you'll get to learn about that method in voting. It's kind of an interesting system. So we're going to let X be our predictor variables. Y is the percentage that each candy won against others. All right, so now let's go ahead and split our data. I'm going to be using the train test split function to do it. So you'll notice that here I'm splitting it up into two groups, 50-50, just because I like the 50-50 way. I think it's a more natural way to go it. And let's take a look. All right, so we've got 42 rows and 11 columns for our training set. And let's see, you have 42 observations for the target variable. Then 43 and 43. Okay, so it's not quite 50-50, it's close. Now from sklearn tree, we're going to go ahead and pull in decision tree regressor because this is a regression problem. If I want to do a classification problem, such as if I was doing like logistic regression, then I would use a classifier instead. All right, so now, when I build my decision tree, you'll notice that for a parameter, I have max depth equal to 3. So what this is going to do is I have what's called stump. It's going to break, and then it's going to break each of these. And that's going to be a depth of 3. A depth of 1 would just be a stump. A depth of 2 is from one break, one splitting of the data. Depth of 3 is from splitting again. So we will have at the end, the terminal nodes, there will be at most 4 of them. Now, just because it has the opportunity to split doesn't mean it's going to. It's going to check to see, does it improve my model to split, yes or no? And then it will make a decision on that. So let's go ahead and fit the decision tree. All right, so now let's go ahead and let's score. Let's see how they compare. All right, so we got 0.68 on our training set, but we only got 0.14 on our test set. That's not very good, not very good. I would not bet my career on this, but we need to work with this if we want to be able to use other more powerful machine learning techniques. One advantage of decision trees is that these are some of the models that human beings can actually use. We can check to see the criteria of a split, and we can make decisions off of them using like a flow diagram effectively. It's for that purpose, it's really nice. If you think about like regression, if I want to be able to use a regression model like by myself to make a decision, I need pencil, paper, I need a calculator, and it's gonna be kind of a pain. A neural network, I can't possibly do that. So if I wanted to build a model that, let's say, you know, a doctor that's going to be going off into a remote area where they will not have technology, I want to be able to build a model to tell them on, you know, what to do for certain, like, let's say, disease symptoms. I could use a decision tree to give them this information without having to give, you know, without them having to have a whole lot of electronics with them. All right, so let's go ahead and do our predictions on our training set. Let's do the predictions on the test set. And now let's go ahead and let's plot. Let's take a look. Let's see how this looks. All right, so we can see that the blue is closer to a straight line, but the yellow, the test set, is just all over the place. I mean, just all over. And we can see that it just really didn't do a very good job. All right, well, let's see what happens if we put max depth of, let's say, let's go absurd. Let's see what happens. All right, so we can see that if I go with a crazy max depth, it gets really, really tight, but the test set is absolutely meaningless. In fact, we have a negative score. That negative value tells us that it's actually worse than, than some other method of just saying like the average overall value is our prediction. But when we look at our training set, we have 0.94. I mean, that's really high. So here, remember, if I see that my training metric and my test metric are far apart from each other, that's a sign that I overfitted. The training metric tells me how well did the model fit on the training data set. The test statistic is my indication of how well it fits on the population. All right, so let's kind of mix this up. Let's see what happens. What if I go with just one? All right, so here it just splits one time, and we can see that it's pretty spread out. You know, over here, the larger values are on the right, lesser values are on the left. Let's keep walking this in. Let's see what happens. All right, and while the test set's all spread out. All right, so let's go ahead and go through, and let's do this a bunch of times. Let's loop through and see what will we get if we go through, say 1, 2, 3. Let's go ahead and put a 4 in there, 6, 7, 8, 9, and 10. So what we're going to do, just to kind of see how these perform, I'm going to go ahead and I'm going to run this for max depth of 1, 2, 3, 4, all the way up to 10. And I want to take a look at the score we get. All right, so that's pretty quick. So let's see. All right, so we have 0.47, 0.29, 0.14, 0.15, and there'll be a little bit of randomness in this, so there'll have to be too much of a trend. 0.08, 0.03. Now, oh, it's negative. So actually it does worse than just like average, you know, saying the average, the population average, or the, excuse me, the overall sample average is the prediction. So once you hit negative, you know you've got crap. All right, so here, the actual best depth was 1. Huh, kind of surprising. So with just 1 split, this data really, so this tells me that no single feature can be split very well if I want to be able to do a prediction. It's going to be a little bit more complicated, more nuanced. All right, so let's see, let's go ahead and, since our best one was 1 with a 0.47, let's go ahead and rebuild our model so that we have a max depth of 1. Let's go ahead and run our predictions. And let's go ahead and plot it all over again. And we can see that's not much of a split, but yeah, it's something, it's interesting. So this is regression decision trees. This really is not a very powerful tool on its own. Its #1 use is really when a whole bunch of trees are combined together. So you kind of have to have a gestalt to pull them together to get a good solid model. It's either with boosting or random forest. The other good feature of this is that humans can interpret this on their own. If I was to go through and I was to plot this, you know, I could show you like all the splits, and you know, it would be good. It would be something that you could use if you were like off in the woods and like, oh no, I don't have a calculator. I need to, you know, do a predictive model, which, you know, like, you know, Doctors Without Borders would have to do at times. So it's interesting, and you know, that's all I got. Take care and stay safe.